Hello and welcome to this presentation of 3D surround views for robots. My name is Birgit Hasenberger from BECOM Systems, and I'm joined by Manuel Haas from Dataspray. We have conducted a feasibility study where we combined time-of-flight technology with deep learning to obtain a 360-degree 3D view of a robot surroundings and detect people in that area. First of all, a few words about the company. So BECOM Systems was originally founded as Blue Technics, and since 2016, we are a part of the BECOM group. By now, we have more than 10 years of experience in time-of-flight development, and we develop and produce time-of-flight systems in different formats. So for example, development kits, we also have our standard off-the-shelf cameras, and we also do custom developments. Our cameras are applied in various sectors, for example, medicine, industry, and also the automotive sector. Today, we are going to focus on robotics, though. So the developments in the industry have brought along new and challenging requirements for robots. They are required to behave more flexibly and autonomously. They are required to tackle complex navigation and handling tasks. We expect them to navigate unstructured surroundings. And there's also the requirement to being able to collaborate with humans. Now, these requirements mean that robots need to perceive their environment as quickly as possible, so with very little time delay, but also in a very robust and complete fashion. So for this feasibility study, we chose time-of-flight technology because it allows us to obtain a perception of the environment in all three dimensions. So a few words about time-of-flight technology. It's a method to measure distances based on the travel time of light. So the scene is illuminated with modulated light, and the reflected light, the phase shift of the reflected light is measured. And from this, we can deduce the travel time of the light to and from the object. And this travel time is directly proportional to the distance from the object. So in this way, we can obtain a distance measurement for each pixel simultaneously and independently. The end results of a time-of-flight measurement look something like the images you can see on the left. So you obtain a depth image where each pixel corresponds to a distance, and also a grayscale amplitude image. The depth image can then also be translated into a three-dimensional point cloud. Advantages of the time-of-flight technology are that it is largely independent of ambient light, and very high frame rates can be reached. Another advantage is the scalability with respect to depth, range, field of view, and also resolution. So on the bottom right of the slide, you can see a list of typical specifications of a time-of-flight system. For the specific application in robotics, this means that we can capture the close proximity of a robot up to a few meters. And in that area, we reach an accuracy in the millimeter to centimeter range. A time-of-flight camera consists of several components that need to be matched and balanced according to the specific application. And this starts with, for example, the illumination that can either be in LED or laser format and might need to fulfill certain eye safety requirements. Then we have the optics, so the lenses that define the field of view. We also work with multiple sensor vendors to make sure that we find a good balance in that aspect as well. Our core competency is embedded processing. So, for example, the calculation of the distance and the 3D point cloud, as well as filters and other algorithms, are happening directly on the camera. We also, so most of our cameras offer several ways to interface, for example, Ethernet or USB. And finally, of course, mechanical integration is also an important aspect where, for example, certain size requirements need to be met, and cooling, of course, is also important. Going back to robotics, where can we actually apply time-of-flight technology in that field? On the one hand, we have navigation, where obstacles need to be detected, and motion planning follows this obstacle detection. Then we have also object classification. So, for example, the detection of people, of pallets, of landmarks, or also a detection of other machines or AGVs. And at the highest complexity level, we have context understanding and interaction with humans. This requires understanding of work processes and also pose estimation and gesture recognition when it comes to interaction with people. The feasibility study we are talking about today focuses on the detection of persons. So person detection finds its application in several different sectors, for example, in a classical industry or warehouse setting, but it is especially important for service robots because these machines operate in complex environments with people who might have not been given special training or instructions on how to behave in the proximity of these machines. So possible environments where these service robots might work would be a supermarket, a medical sector, or also the home. So the setup for our feasibility is as follows. We used 4 time-of-flight sensors to obtain this 360-degree view, and those provide us with amplitude images and depth images of the scenes. Those data are then processed on a processing platform, our multicam hub. We then apply a deep learning algorithm, a pre-trained model, to the data to recognize people in the scenes. So from the hardware side, as I said, we use 4 time-of-flight sensors. Those can be connected to the processing platform using FPD-Link, and they are equipped with a 110-degree lens. Now, with these 110 degrees, we can cover a complete surround view if we use 4 sensors. However, because time-of-flight cameras have an active illumination, we need to take measures to avoid interference. And in this case, we use the hardware trigger to synchronize the cameras, which helps to avoid interference, and also it also helps with the registration of the point clouds. The second part of our setup is the processing platform, the multicam hub. It is equipped with several interfaces, including 4 interfaces to connect time-of-flight sensors, and it is based on an NVIDIA Tegra TX2. So there are several processing steps that the hub goes through. For example, starting with synchronization and triggering that I've mentioned earlier, and also data acquisition and the calculation of the distances. In addition, we also perform corrections and filtering on the hub and the calculation of the 3D point cloud. If necessary, also registration and transformation of the point cloud can happen on the hub. The hub also provides enough computing power to perform embedded inference, and the information we gain from that can then be transferred to an application or simply output as data. So for the first few steps that I mentioned here, we've already covered roughly. So for the second part, the deep learning part, I will hand the mic over to Manuel Haas from Dataspree.
Yes, thank you, Ms. Hasenberger. So we've seen that deep learning and time-of-flight technology can be used for a variety of use cases, but the question arises how to develop those deep learning algorithms. And for once, you can use expert like us from Dataspree to do your project, but internally and also externally with our customers, we rely on our deep learning DS suite for the development of the deep learning algorithms. With that, it is possible to develop custom deep learning models without too much expert knowledge, since we have an abstraction of the best practices and a big variety of models to reach certain requirements for the inference, like speed or the individual task. All this is done via user-friendly graphical interface, and therefore it is a low-code to no-code development interface. In that we display the whole development cycle, which I go into in the next few slides, from data annotation and model training up to deployment. Yes, so with every deep learning application, data is the basis of it. So we need to acquire a lot of data from the setting we want to use the algorithm in. After that, we have to tell the algorithm what to focus and what to attend to in the image. So that is a manual part where we need to manually annotate the images with metadata, which is then used for the model training and before deploying the trained model on the device. An interesting point here is that if we have a shift in our environment and maybe the accuracy is not good enough, we are always able to acquire more data, annotate them, and fine-tune the model on your certain setting. So in the next few slides, I will show you the process, how this is done, starting with the annotation part. So in here, you see our annotation tool within Deep Learning DS. In this case, it's an object detection, where we have to show the algorithm where persons are located in the image. In this false colored image, you see the amplitude image from the time-of-flight camera in the green channel and the distance image in the blue channel. We have several helpful tools to accelerate this tedious process. For example, tracking, which can be used with consecutive video frames, or automatic annotations, where a pre-trained model can be used to make suggestions where people already in the image. After that, we can train our models. For that, you can choose different settings and also compare them afterwards. So, for example, in here we have shown 3 models which are being trained, and we compare their accuracy with certain metrics. In the object detection domain, those metrics are mostly the mean average precision, which is a measure for the detection accuracy if every person in this case is detected in the image, and whether the size regression is accurate or not. Metrics tell you only so much. You can see that most of the training data, or in this case test data, is accurately inferred. But to make sure that it's really the case, we can also do a qualitative analysis, where we can see the actual results on the test data used for the model training and evaluation. In this case, you see all the persons are accurately detected, and we have certain options to make sure that those is really the ground truths from the annotated data, or to play with the selectivity of the model to have a way to see whether the model is generating false detections under a certain threshold. This is interesting in different applications. For example, in one case, you want to have, or you want to be really sure that the detected object is a person and no false positives are generated. And other settings, like the HEV settings, false positive maybe not that of an issue, but if we miss a person, that can be a whole other story. But now let's go to the results. In this videos, you see the setting of detecting two persons, where we can accurately detect the persons in real time. And since we have the depth information from the time of flight camera, we can also see how far the person is away. This is also working with occlusion and different lighting condition in the infrared. The inference is happening in real time on the multicam hub of BECOM, and in this case for up to 4 cameras. And here you can see those 4 cameras for a 360-degree surrounding view, and you can see the model is able to detect the persons in a variety image differences. For example, in one case, the amplitude channel is really dominant, while in other cases, the information is mostly given from the depth image. Also, if the person is occluded or in the borders from the image, it can be still accurately detected. Again, handling occlusions with ease. And in a second, you will see a person picking up the box, and the algorithm can differentiate between the person and the box and only does a size regression for the person. So in summary, time-of-flight technology combined with deep learning has a lot of advantages for obstacle and object detection, since it's very robust to different visual variations like lighting condition or, for example, color. And therefore, it can be reliably used in different settings. Also important to note is that we can do real-time embedded inference on a system like the BECOM multicam hub with up to 4 cameras. And of course, with our deep learning DS platform, it is possible to flexibly expand the type of object and obstacle to different things like pallets or other boxes, for example, or other HEVs. And this can be also done simultaneously. So, for example, you can have persons, pallets, and boxes detected separately with one algorithm. So, thank you for listening, and I hope you're interested. So, please contact the BECOM Systems or us from Dataspray with the links given. Thank you.
Thank you.